So it's a pleasure to give this talk to this audience. I've wanted to give this talk to you guys for a long time. I was just checking on Google Scholar. BLAST has been cited 50,000 times. And generally I'm credited with the algorithm behind BLAST. And so what I want to do is I want to tell you the story of how I was working on basically an approximate match algorithm using an index. Basically exactly the problem that Alberto indicated. How do you use an index to do approximate matching? And it was the sequence of ideas that I was looking at that basically had an interaction with David Lippman that led to BLAST. But I'd like to show you the kind of underlying theory because I think it's interesting. And unlike BLAST, that paper has only been cited 213 times. Probably 40 of them by me. So I'd like to kind of show you this work because I don't think that many people know it. And so let me just start just to make sure. So for this audience, I don't think I need to explain what the approximate string search problem is, but just so we have some common terminology. The query, the target string is a sequence A, where n is exceedingly long and the millions or billions. And the idea is you have a query sequence Q of length p, which is quite a bit smaller than n. And the idea is to basically, given a scoring function and a threshold, find all the substrings of the target A, say M, that have a good alignment to the query. And in this talk, the measure of similarity between two strings will be just simple Levenshtein. So unit cost, mismatch, insertion, and deletion. And just to make sure that we're all on the same page, if this is the long target string A and this is the query, then here's a match involving three differences. So I would call it a three match in absolute terms. But what's very important is a lot of times I'll talk about it in length relative terms, okay? So the query is of length 12, and there are three mismatches, so I'll also call that a 25% match, okay? So as a function of the length of the query in relative terms and length relative terms, it's a 25% match. One other little piece of background, everybody I think knows what an edit graph is. So you take the two strings you're comparing, and you put them along these two axes, you build this nice regularized structure, and effectively, basically every horizontal edge represents a deletion, every vertical edge an insertion, and every diagonal edge either a substitution if the characters are different, or a match if the characters are the same, which I've denoted by purple edges. And effectively, one can compute the distance from the origin to any one of the vertices, so you start at 0, with the dynamic programming algorithm, which in this case reveals that there's one difference between these strings. But the way I really like to think about it is I like to think about paths in the edit graph. And this graph by induction is constructed in such a way that if you take any path, the path represents an alignment. So this yellow path here represents aligning A with A. This A is inserted, and then you align the B with the B. And in the dynamic programming path, it would correspond to this. And of course, the difference between the two strings is 1. So in a larger schematic, for example, if I was aligning if this is A and this is my query and this is that alignment that I showed you in an edit graph schema, I'll just draw a squiggly line that means that basically there's a path from here to here which aligns basically the corresponding strings in the projection to the two axes. Okay, so that's the setup that we need. So that's the nomenclature. Okay, so let me start the story. Okay. So this story starts in March of 1988. Webb Miller and I were new to computational biology, and we hosted our first meeting on computational biology at the Lister Hill. And it was March 26, 28, 1988, and these were the people that showed up. And you'll recognize a lot of the names. Gaddy was there, Zvi was there, Sam Carlin, David Lippman, Chris Sanders, Mike Waterman, Esco. Okay, a lot of people you know, actually. And a few you don't know, but who were shakers and movers at the time. And this was a very exciting meeting for me as a very young guy. And Galil, Zvi got up and gave a talk, and he asked 2 questions, I think from his open stringology questions, although I'm not sure about that. And so he gave a talk about suffix trees, and his first question was, could you get rid of the annoying dependence on alphabet size sigma? Right, there was this problem that you either had to spend n sigma space, or you had to have the sigma in the query time, right, if you wanted to build that thing. So that question has since been answered many ways, but the first attempt at answering that question actually led to suffix arrays. So if you want to know how suffix arrays happen, okay, I guess V was responsible for it, right? He got me to thinking about how do I get rid of that sigma. And this was, if you actually look at the complexity of the suffix array paper that Udi and I published back in 1990, and you guys have since gone on to do wonderful things with it. So, but it was the second question that actually captured me more, which was basically Alberto's question, which is, if you give me some kind of an index, like a suffix tree or a suffix array, can I do this approximate matching problem more quickly, right? So you give me an index over the big query, over the big target, A. Can I efficiently do that, okay? So, and one thing, just so you know, is I guess maybe, I don't know if I need to do this piece, but it will turn out that in the algorithm that I'm going to give, we're going to be looking for strings of size the log to the base of the alphabet n, okay, so log sigma n, okay, is going to be the query size. And if that's the query size, then just simply building a very simple index where I have an index of size sigma k, so for every potential k-mer, okay, I have basically the code of the k-mers. I have an index for each one of them. And then I'm going to keep the positions in the array that have that thing in a nice ordered way. So for example, if I want to know where all of the occurrences of k-mers with the code C are, then I simply go to index C, I go to here's the first one, and I'll find the position in the text of the first position, and I'll just keep listing them off until I get to the next pointer or next finger. And I'm not going to spend a lot of time on this, but the point of the matter is that this can be built in linear time in basically 2 very simple sweeps, and I'm not sure what happened to where's the second part of the slide? I'm very sorry, there's supposed to be scan 2, and it's missing. I'm not sure what happened to it. But anyway, the point of the matter is that this thing can be built in order n plus sigma k time, and if you choose k to be equal to log sigma n, then the whole thing is order n. So it's basically 2n integers, right, is the index, and that's the fancy indexing structure I need for this algorithm, okay? All right, so the first idea I had was basically seed and extend, and let me show you how that works. So the idea is that, so I think everybody here knows what a filter is. Whoops, sorry. And so a filter is an algorithm that eliminates a lot of what isn't desired, but it has the property that it retains everything that you are looking for. So the idea is it eliminates a great deal of the things you're not looking for. There may be some things that you don't want that are still there, but certainly everything that you are looking for example, all the approximate matches to the query, are still in the set of things reported. So it winnows it down. And it's somewhere between an exact algorithm, which is what we spend most of our time designing, and a heuristic where you can make errors in both directions. But filters basically allow you to have a very efficient deterministic algorithm, right? And probably a lot of people in this audience have done that, which is that the idea is you run the filter, and the filter is hopefully really fast because it's using some simple criterion to take this huge bolus of data and get it down to a thinner stream. And then you can always get an exact algorithm by taking whatever exact algorithm you want and running it on what's left, right? And hopefully if the filter is fast, then that gets rid of things. So there are a lot of filtration ideas for approximate match. Now, interestingly, in 1988, there were very few of them out there. Most of them were coming out at the same time that I was doing this work, but a lot of people have spent time basically working with exact matches to k-mers. And what I was thinking about at that time was instead, kind of after Svea talked about it, was to look for k-mers that are a small distance away. In other words, involve one or two differences. So in other words, instead of looking for exactly each of these small strings, I'm going to look for something that's in the neighborhood. In other words, I'm going to look for I'm going to look for all of the, if I'm looking for something that's approximately close to W, then I'm going to consider D differences. I'm going to generate every word that's D differences away from W, and I'm going to look for those exactly, okay? And just to get an idea, the size of the neighborhood, how quickly does the neighborhood grow? So obviously the zero neighborhood of a K word is 1. There's one word, W. But if you start adding it, basically a very simple calculation is there are K positions. I'm going to edit D of them, and then at each position there are 2 sigma possible edits. Sigma minus 1 substitutions, sigma insertions, and 1 deletion. That's 2 sigma, right? And so this is a very crude bound, although it's not exactly right. But what it shows you is that as D gets larger, this thing's going to grow exponentially, right? The size of the neighborhood gets big very fast, right? And you would think, well, that's really bad, right? Why do I want to look for a lot of words, okay? But here it's a little bit counterintuitive. So let's take a look at why it's powerful. So this is basically the kind of the probably the most important part of the talk, because it shows you the power of the idea of neighborhoods instead of exact matching. So suppose that we are looking for the query is 40 symbols long, and we're looking for a 3 match. Okay, it's very, very carefully chosen. Okay, if I take the query and I divide it into exactly 4 substrings, each of length 10, right? Then if I'm going to align it to something in A, notice that I have only 3 differences. So one of these 4 words must exactly match, right? One of them must exactly match by the pigeonhole principle. I only get to put in 3 edits, and so one of them must be clean. Okay, I think that's obvious enough. And if you think about that, then this is really a problem. There's more of the talk missing, and a really important part of the talk missing. I mean, there's an entire piece of text that's supposed to be there, and it's not. Yeah, see, it's not even there. I don't know why it's not there. So let me just show it to you this way. All right. So this is my workaround. No, don't send it back because I won't see it. I won't see it. It doesn't show up. So let's go back. Okay. So it is there. I have no idea what's going on with this version. But see, so what it says is that basically I'm looking for 4 different words, and I'm looking for tenmers. So how often does a tenmer occur at random in a string? Sigma to the 10th, right? And then I'm looking for 4 of them. So every sigma to the 10 over 4 positions, I expect to find a match, right, in a random text, which is basically every 250,000 base pairs of DNA, I would find a match if I was working over DNA. Now, let's consider then, instead, using the idea of a neighborhood. So what I'm going to do is if I use the one neighborhood, then I can divide this query of length 40 into 2 parts, okay? And by the pigeonhole principle, at least one of them involves only one difference, right? Which means that if I generate the one neighborhood of this 20mer, I'll capture whatever this string is. Or if I generate the one neighborhood of this thing, I'll capture an appropriate string. So in other words, to find basically all of the places where there might be a 3 match, what I do is I generate the one neighborhood of these 20mers, right? There are 2 of them. But notice that how often does a 20mer match? Well, sigma to the 20. Okay, so for DNA, that's another factor of 1,000,000, right? Okay, so there's going to be 1,000,000 fewer frequency matches. The trade-off is that instead of looking for 4 things, I'm looking for 2 times the size of the neighborhood. And the neighborhood, by my estimate, contains 80 words. Actually contains 66, but we'll say 80. So that's 10 to the 12th divided by 2 times 160 is 3.12 times 10 to the 9th. Okay, you can't see it, but it's 10 to the 9th. Can I move that? And so that's basically 10,000 times more specific, okay? So by accident, right, it's a much stronger filter, right? On a random text, it's only going to light up one every 10,000 times less often. The trade-off is that I'm doing 80 times more lookups, right? So basically, I'm going to be at least 125 times faster, okay? At least, okay? And that's the power of it. So let me try going back into the talk. Is this the correct button? Yes? Okay. So sorry, but I'm going to, as long as things are missing, I'm going to have to go back. Okay, so to look at that in kind of edit graph terms, all right, the idea is that I've got my query, okay, and let's just say I divided it into 4 parts, okay. Then what am I really doing? I'm generating neighborhoods of these 4 parts, let's say, and looking them up exactly, okay? So I'm finding these words, okay? So I'm finding positions where I know there's a match. Oh, did I go backwards somehow? I did, okay. And if I'm doing neighborhood matching, say I'm looking for the D over 4 neighborhood because I'm looking for D matches. So by my pigeonhole principle, these guys should match, should have a D over 4 match. So that's a little bit bigger, okay? And then the idea is, so I look up all those positions, and then what do? Well, at least in incarnation 0.1, what I did is I just did dynamic programming around those hits, right? So I find them, I do dynamic programming on the few hits that I have, okay? And basically the total time is basically the size of the pattern times the size of the neighborhood, which I'm calling Z of K. And then basically the dynamic programming is D times P time, and then they're P over K of these things, and H of K is the frequency with which I'm going to find a match, okay? So I've got 2 interesting kind of parameters here, the size of the neighborhood, and how often, when I generate a neighborhood, am I going to find a match, okay, in the query? How many matches am I going to find in a text of length n if I generate the neighborhood, the epsilon neighborhood of these segments, of these k segments, where the segments are of size k? And the interesting thing is if you think about it, in terms of k, the neighborhood size is going up, right? As k increases, neighborhood size is going up exponentially. But as k increases here, the number of hits per k segment is going down. So there's a trade-off, right? So the question is, what's the optimal value of k to kind of minimize this term, right? And it turned out I couldn't solve it analytically. But, goodness gracious, it's not showing again. But is there a way that I can at least have this without the... There we go. Okay. Yeah, well, that's all right. As long as you can see it all. So they're both functions of A. And the interesting thing is what I was able to prove is that basically the answer is you want k to be slightly bigger than log sigma n, okay? So log sigma n is going to turn out to be very important, okay? I already started by claiming that I was building an index over that size. But it turns out that it's something slightly bigger than log sigma n. In fact, what I was able to show is that as n over p approaches infinity, in other words, if the text becomes exceedingly large with respect to the pattern, then the optimal choice of k basically converges to log sigma n from above, okay? I was able to show that, but I wasn't really very happy with that, and so I basically sat on that for a while. Then what happened is I'm now visiting, so basically I sat on that for about 6 months, couldn't get anywhere. And, but in May '89, I happened to be at the National Institutes of Health. Okay, and I was still a cigarette smoker. So here I am. This is the National Institutes of Health. It's May 18th, a Thursday, 1989. I'm having a cigarette out here, okay, which is right there from Google Maps, from above. Okay, and this guy comes out, okay, who was running the center, David Lippman, comes out and says to me, "Hey, Gene, I saw this article, okay, in Science, okay, from the May 12th, okay, about this new chip that Kwang Yu is talking about, and Lee Hood's in here saying, wow, this is great, this chip is going to make searching so fast, systolic array." And, you know, I was a brash young guy, I'm sitting there smoking my cigarette, and I'm going, I don't believe in that hardware stuff, okay? It's like, we just got to be smarter, okay? I've got some ideas, okay, where we can definitely beat this chip, okay? We can just do it with a regular machine. Who wants to build an ASIC? Okay, and that's what really started it. So I started telling David about this thing that I just told you about and what I had done. And David's known for having done FASTA, which was one of the early search engines for proteins. they said, well, I'd like to do something with protein, so let's sit down and think about it. And basically what happened is we very quickly, basically through that summer, worked out a number of kind of heuristic adaptations of what you just saw, okay, to basically give rise to BLAST. So BLAST is basically a seed and extend, okay, which is exactly what I showed you, with a couple of caveats, which is that instead of partitioning the word into k-mers, we basically just took every k-mer, okay, all overlapping k-mers, okay, because we were going to look at neighborhoods, and instead of looking at neighborhoods under Levenstein, we wanted a biologically relevant measurement, so we were taking neighborhoods, because the context works for any metric, right, or any measure, okay? We were looking at neighborhoods under the PAM 120 scoring scheme, okay? So we would build a set of all of the words in the neighborhood, and then instead of using an index, we ended up using a finite automaton to actually scan in linear time, okay, which I wasn't that happy about, but that's the way, it's a longer story. And then the extend, instead of actually kind of then doing dynamic programming across the entire protein, all we did is we took that seed het, and in the matrix we tried to extend it, okay, with a simple Hamming distance that would stop when the score drops too much. It's definitely heuristic, not guaranteed to find everything that you're looking for, but it was blazingly fast, okay, compared to anything else that was available for using the databases. Okay, and that was BLAST. Okay, and BLAST. So the name BLAST, which is a kind of a violent name, was inspired because I had used it. I was calling my thing SLAM for sublinear approximate match. So we had to have an equally violent name. Okay. Anyway, all right. So that was kind of basically BLAST. And then in the meantime, I'd finally gotten kind of the right insight that I wanted. So I'm going to go back now to the story of how to do approximate matching with the index. So let's imagine that here's a word, W, that matches V with K errors. And W is going to be the query, and V is a target substring. So if I divide W exactly in half, okay, we'll call this W0 and the second half W1. And then what will happen is W0, and I have an alignment between these two things involving K differences, then W0 is going to align to some prefix of V, and W1 is going to align to some suffix of V. And again, by the pigeonhole principle, one of these two alignments must involve less than K over 2 errors, right? Must, by the pigeonhole. You've only got K errors to spread around. You put, one of the two buckets has to have less than K over 2, okay? Let's suppose that it's V1, okay? And so this is basically a proof of the following very simple little lemma, which is that suppose that W epsilon matches, so K is equal to epsilon W, okay, V, then either W0, the first half, has an epsilon match, because W0 is half the length, and it's half the errors, right? So epsilon is the same, right? That's why it's important to think in relative terms, right? In relative terms, it's still an epsilon match, right? Because this guy is half the size, and the number of errors is half. So the ratio is still epsilon, okay? Has an epsilon match to a prefix of V, we'll call it V0, or W1 has an epsilon match to a suffix, okay, call it V1. Okay, so one of the two must be true, right? Okay, and then what you do is you just simply apply induction, right? Suppose that it was V1. Then I take W1 and I split it in half. And again, what must happen? Well, one of the two halves must match. Let's suppose that it's this one. At rate epsilon, right? It must involve K over 4, right? And so on, okay? Down to, say, here, which is K over 8, okay? And the way I'm labeling these things, then, is that I'm just saying, okay, so W epsilon is W, and W101 is the left half, and then the right half, and then the left half of the right half, right? So you see I just have a little binary indexing string, so W beta A is this recursively, okay? And the important thing is that suppose then that W epsilon matches V. Then by induction, what I know is that for, say, some string alpha, okay, let's say, however, I want to keep subdividing until I have pieces of a size I like, okay? And let's suppose that that string is of length alpha, okay? Then there's got to be an alpha, some path through this tree of divisions, such that for all of the the elements on the way back up to the root, or prefixes beta of alpha, it's true that W beta has an epsilon match to a substring of V. And, again, the subdivisions are either prefixes or suffixes, right? So what I want to do is I want to use this in reverse, right? Which is suppose that what I have then is the following idea. If I'm looking for an epsilon match to W, then I can take, say, all of these eighths of W, and I can look for epsilon matches to them. Okay? And if I find one, then what I know is that if this is actually an epsilon match to W, then every ancestor on the way back to W must epsilon match, right? Got it? So that's the important part. So let's use that then in what I call a seed and extend by doubling. Okay? So in other words, the last time what I did is I just found the neighborhood words, and then I went boom, try the whole thing. Now I'm going to sneak up on it, okay? So here's what I'm going to do, okay? So any epsilon match of Q must have an epsilon match to at least one seed segment of size K, okay? So let's just imagine that, all the math works out and the divisions work out. And let's suppose that I divide my thing down into 4 pieces. And these are the seed sizes that I want to use, okay? Then what I do is I generate the neighborhoods of these yellow words, of these 4 yellow words, and I look them up exactly using my simple index. And effectively what I'm getting is I know that I'm getting little regions, right, parallelograms, where there must be an epsilon match. What I then do is I then double, okay, according to the lemma. So for example, this guy is here, so I double to its ancestor, which covers these 2. This guy here, I double to get its ancestors, and so on. So I have these larger parallelograms. They're twice as long and twice as big, so it's 4 times as much computation on these guys. And I check them, okay? And I say, are you an epsilon match? I use dynamic programming. And a lot of them fall away, right? If you're looking at, for example, a text that's random, you have no reason to believe there are any matches in the text, right? Because this is the filter. Wherever there is a match, there is a match, okay? But let's assume the idea of the filter is to get rid of very efficiently everything that doesn't match, okay? So assuming the text is random, right, most of these guys will drop away. 1 or 2 of them will survive. And for the ones that survive, I double again, okay? And I keep working my way backwards, right? Okay? And I check them, and then maybe this is what happens, okay? So now it turns out, and I can't, I don't have time to set up the whole thing, but it turns out that against a random text, the number of these guys that survive, they're dropping like flies. I mean, they're dropping hypergeometrically, right? The number of these checks that actually survive, the probability is going down. If it's 1 over x for the first check, it's 1 over x squared, then 1 over x to the 4, 1 over x to the 8th, right? The mathematics, it telescopes hypergeometrically so that really the time is bounded. I'm sorry, I'm blowing the camera work, aren't I? The time is dominated by the first step, okay? Because basically the time and the extensions are dominated by that. So basically it drops hyper-exponentially, which means that if I've divided it into k pieces, then there are p over k pieces. I'm going to get an average hit frequency of hk on a text of length n, and the first dynamic programming step is k times epsilon k, right? So I'm down to dk times hk, and compare that to what we had previously, okay? Good, okay? All right, so that was the first thing, okay? And I was pretty excited about that. So now I had a much more controllable term. So the problem then was the flip side. It looks like a little innocent problem, but the problem is how do I generate all the words in a neighborhood, okay? How do I actually generate all the words in a neighborhood, right? A little exercise in dynamic programming, okay? You probably already got it, okay? But let's actually note a couple of small things first. So the first thing is I want to generate what's called a condensed neighborhood, okay? It's a small change, but it's important. So I'm going to generate all the words that are less than or equal to d differences from W. But further, there's no other word that's a prefix of that word in the neighborhood. Okay, so let me show you an example. Here's the one neighborhood of ABBAA, okay, over that 2-letter alphabet AB. but if you look at this, okay, suppose that I look up everywhere I find A, B, A in the text, I immediately know that I have A, B, A, right? So why am I bothering to look for this? I don't need to, right? Because I found it anyway. And so if I get rid of all the words that have a prefix in the same set, I get rid of all those guys, right? Okay? And that turns out to give me an asymptotic reduction, okay? So our goal then is to find all the words in the condensed neighborhood, okay? But how do you do that efficiently? Including finding them in the index. Then the idea, which I'm sure a lot of you already have seen, is that you compute the rows of the dynamic programming matrix as one traverses the trie of all the strings. So let's go ahead and do it, okay? So let's imagine that here's W. I'm going to generate the one neighborhood of A, B, B, A. So here's the first row of the dynamic programming matrix, and I haven't spelled anything. V is a question mark, okay? So let's try an A, okay? If I try an A, okay, so if I make this A, then this is the next row of the dynamic programming matrix. Okay, there it is. And everything's good because I'm still less than 1, okay? If I try another A, that's the next row, okay? Now, it turns out that if I try an A, I'm going to get to something where there are no 1s or 0s in the dynamic programming matrix. That means I can't possibly have a 1 match, right, to something. So something that begins with A isn't in the 1 neighborhood. But if I try a B, I'm good. And if I try an A, I'm good. And if I try another A, I'm actually down to the point where I have a 1 in the corner. Okay, great. That's in the 1 neighborhood, right? Okay, good. All right. First thing, you only need the band that's plus or minus 1. If I'm only interested in the values that are between 0 and 1, okay, or between 0 and k, right, then I only need to stay in between diagonals minus k to k, right? Or d minus d to d, excuse me, minus d to d. If I'm looking for d differences, right? In this case, we're looking for 1 difference, so I just need to be in diagonals minus 1 to 1, because if I step off more than d diagonals away from the 0 diagonal, right, I've got more than, I've taken d plus 1 insertions or deletions. So I don't need to compute that part of the matrix. So an obvious optimization is, instead of spending order k time, right, because each one of these takes k time to compute, I'm just going to spend order d time computing the purple values, because those are the only ones I need, right? I just need that band, right? Very old observation. Okay, so we do that one, okay? All right, so that's what I compute. So now I'm spending order d time per step, okay? Now, all right, and then let's carry on, okay? So we continue the exploration, okay, and we find this tree, okay? All right. This was a difficult slide to arrange. Okay, but if I think about it some more, I'm actually wasting a lot of time, because any entry where all the values are greater than or equal to d, why am I doing dynamic programming? If I have no entries less than d, if every entry is equal to d, then I have no more. I don't have any more deletions, right? I'm done deleting, right? I can't make another editing mistake. So once I get to a vector that has only things greater than or equal to d, I can stop, because I know that the rest of it must be equal, right? An extension of that d. So what I'm going to do then is I'm going to mask all those out. So see, it gets rid of a huge amount of the tree. And in particular, one of the really important things is that the remaining tree is in the case of this 2-letter alphabet, is binary. And in the case of a sigma, an alphabet of size sigma, it's a sigma-ary tree, right? Because every internal node, right, has a d minus 1 in it, which means I can take any letter, right? Because I get 1 deletion, right? So I'm going to have sigma descendants, yes? So I'm never wasting any time, okay? And when I get to these guys, okay, what am I going to do? Okay, the ones, well, for example, let's take this guy over here. I have 1, 1, 2, right? What are the only answers? So I have 1s here and there. Well, I have to basically extend with things that are exactly equal to the remaining suffix of the string, right? Those are the 2 extensions that I can get. Those 2 words are in the neighborhood, okay? So there they are, okay? See them? Okay, I'm going to do that with everybody else. Okay? And this guy, by the way, is done because it's got a 1 in the corner. Okay. So we're looking really good, right? And notice that those are fixed suffixes. So in terms of Kramer arithmetic, right, I can compute the tuples in just order one time because I know the tuples of all the suffixes. I just add it on, right? So it's going to be very efficient. But we do have one small problem, which is that this guy here, ABAAA, is a extension of ABAA. Oh, problem, okay? So what we need to do is we need to look at these, right? And if any of these is a prefix of any of the other ones, then I need to not look at that one because it's not in the condensed neighborhood, right? And I don't have time to tell you the story, but you guys should love this part of it, right? Which is that it involves the Knuth-Morse-Pratt failure automaton. And if you use it, you can actually get rid of those things at no additional overhead. Okay, so sorry, I'm not going to tell every single piece of the story, okay? But I thought that was kind of cool, right? That, yes, it uses something else we know and love, okay? But you can do that. And the bottom line then is that this is a sigma array tree in which I'm getting a word in the neighborhood. I'm getting at least one word in the neighborhood, sometimes more. And so the total amount of time, the total number of nodes computed is z, because it's bounded by the number of leaves, and there are less than z leaves. And I'm computing d time to compute each node. So it's z times d time, right? The size of the neighborhood times the difference, okay, that I want in that neighborhood, okay? Okay. So that actually, it looked like a very simple exercise at first, right? But notice that there were a few subtleties, okay, to getting the result. Okay, so the finale now is to put it all together. How am I doing on time? Am I doing all right? I have 10 more minutes, 15 more minutes. 20. I have 20. Oh, I'm gonna finish it. All right. Okay. All right. So it must be the very strong coffee. Okay. So how big is the condensed neighborhood of K? Okay. I gave you this kind of crude bound, but it turns out I spent a lot of time on this, and basically one thing I did. So I looked at basically trying to develop a recurrence for the number of non-redundant edit scripts. So I looked at kind of edit script sequences that would go left to right across the thing, and I removed certain obvious things, like I don't want to do a deletion and then immediately follow it by an insertion of the same character, okay? No point in doing that. I might as well just do a substitution. I don't want to do a deletion followed by substitution because I can always get that by doing the substitution followed by the deletion, an insertion followed by substitution, or an insertion followed by deletion, which is a no-op, okay? So I got rid of those things. And I worked out this kind of very complicated recurrence, and you can read the article for a proof of this, okay? And at the end of the day, okay, that's just it's too hard to understand in real time, okay? The important thing is that what I basically did is this is a recurrence that counts the number of non-redundant scripts. So this is the number of scripts for words of length k that involve d differences, right? And you can see I've worked out this recurrence that basically is based on this idea of removing redundant scripts, okay? And then I asked the question, how big is it, okay? And so I had to solve this bloody recurrence, okay? And I think 2 weeks later, okay, I finally came out with the fact that I could bound n epsilon k by a constant times this term alpha, which depends upon the epsilon, now I'm using a relative term, to the kth power, okay? And it turned out that this term, okay, to the kth power is sigma to this weird term power epsilon, where power of epsilon is this thing, okay, which is a function of c of epsilon, where c of epsilon is this thing, okay? All right? Yeah, hey, okay, it's true, okay? Now, it took me a long time, okay, to get that, and it's kind of completely counterintuitive, right? So basically what we've got, though, is the way to think about it is that I've got a word of length k. The size of the neighborhood is basically the kth power of this term alpha epsilon, where alpha epsilon is this kind of complicated thing. So, and it also turns out that on the converse side, I looked at what's the probability that in a random text I would find a W and an epsilon k, and that turns out to be 1 over beta epsilon k, where beta epsilon is again sigma, but now 1 minus this function, power epsilon. So I bounded kind of both properties. Now, so basically now I resorted to the computer and I said, okay, show me what power epsilon is, okay, for an alphabet of 4, okay, and for an alphabet of 20. And the important thing is that epsilon, technically, this is not a very good plot. Epsilon starts at 0. Power epsilon for 0 is 0, and it slowly rises, it's concave, and at some point it crosses 1, okay? But for example, for DNA, it doesn't cross 1 until you get to epsilon at 33%, and for proteins, it crosses 1 at 57%, okay? And we'll see why that's important in a minute. So let's forget about the complicated math behind power epsilon and just know that it's this concave increasing function, okay, of epsilon, okay? Okay, somehow or another I got something. And there could be a better bound. I don't know. I mean, this is just the bound I was able to get. And the point of the matter is that what I found interesting about this actually when looking at it again recently is that in some sense the size of the neighborhood is alpha to the k, where alpha is this thing, okay? But what is alpha? Let's think about alpha qualitatively as a function of epsilon. When epsilon is 0, okay, this is sigma to the 0, this is 1, okay? So the 0 neighborhood of k is order 1, right? Perfect, okay? As epsilon gets bigger, right, then alpha starts to get bigger, right? Gets bigger and bigger and bigger, right? And so if you think about it, it kind of makes sense, right? Because if you're finding matches to words in the neighborhood, right, how specific are they? Well, I've got this word of length k, but now I'm allowing deletions in it, so it's kind of soft, right? How soft is it? Well, one way to think about it is like every position is like weaker, right, than is generating several terms, right? It's generating alpha terms, right? Is a very simple way to think about it, right? Is that every position, there's more than one choice for that position. There's not 2 choices, there's sigma power epsilon choices for that position effectively, right? It's kind of a nice, easy way to think about it, right? Even though you're doing insertions and deletions, right? That's kind of what this little theorem says. In the converse direction, for the probability, right, it's 1 over beta k, where this thing now, if you think about it, when epsilon is 0, this thing starts at sigma. So what's the probability of finding a word in the 0 neighborhood of k? It's 1 over sigma k, right? Exactly what you expect. Now, as epsilon gets bigger, right, what happens is this thing becomes smaller, okay? And so in some sense, the specificity is getting weaker and weaker and weaker, right? There are going to be more and more words that match, and so each position is effectively less specific than sigma, right? It's sigma minus 1, maybe it's sigma. So it's kind of a nice, easy way, right, to think about what are the combinatorics or what are the statistics, right, of matches. We're basically in what Waterman would call the logarithmic regime. Okay, now here's the thing. Yeah, I love k equal to log sigma n. Okay, and now it's really going to come home because when k is equal to log sigma n, then a little mathematics will show that this is n to the power epsilon. Okay, just basic mathematics of logs and powers. And the probability of W, okay, is going to be n to the power epsilon minus 1. So notice that this is n to a power that's less than 1, right, for most values. In fact, it's 0 and going up, right? So it's sublinear, right? Like if at 10%, it's like n to the fifth, it's the fifth root of n. It's n to the 0.2, right? It's much less than n. And in fact, if I bring it back to the parameters of the algorithm, so remember, z to the k was the size of the neighborhood, and h of k was the number of matches I expect to find in the text of this thing, and so that's n times this puppy. Oh, it's n to the power epsilon. It's the same thing. Okay, so zk and hk, when k equals log sigma n, are the same. Okay, they're n power epsilon, And n power epsilon is a sublinear function of n, right? It's n to a power less than 1 for most values of epsilon, right? Okay, so, and we return to the complexity of the algorithm. It's basically, it was dzk to generate all the words, and dk hk to actually do the doubling, the doubling extension strategy. This dominates, and that's d times n to the power epsilon times log sigma n. So what we have is we have an algorithm that is sublinear in n, truly sublinear in n to the square root, a square root of n, fifth root of n, right? It all depends upon what power epsilon is. It's very efficient when epsilon is near 0, right? And it gets kind of progressively slower and slower. And it's going to be order n when epsilon is 33% for DNA. And it's going to be n when epsilon is 56% for proteins, right? But prior to that, it's very efficient. In fact, this is some very old timing data, but this was the timing for SLAM versus kind of all the other approaches, given that the index was computed for DNA and for proteins. This is very old stuff, okay? And the other nice thing about the doubling strategy is if there are real hits in the database, then they only take P times D time. In other words, the Ukonen-Myers time, right? The order ND time for the hits. So, but this is a provably, this is an expected time complexity that's provably sublinear in n, okay, right? So I don't know, are there any others, results like this? Well, I'll ask it. You can tell me during the questions, but I've been waiting for somebody to kind of come up with this or see something like this, okay? So basically what was behind BLAST then was really I was trying to come up with a way of answering Galil's question, which is how do I use an index in a way that gives me leverage, right? And here was a way, okay, that allowed me to do it in truly sublinear time, okay? And as far as I know, I haven't seen it. So, and the result was really finished in 91, but it didn't actually appear in Algorithmic until 94 because the journal was so backlogged, okay? It didn't actually show up. And if you're actually interested in this, I suggest that you not read this, that you find me on the web, and you find my URL, and I've got a link to this paper, which appeared in Computational Biology last year, where I actually wrote this story with all the mathematics, and all the details are in there, okay, including the proofs of the theorems, and I've done it, I think, in a nice kind of, well, I hope you like it. I thought it was an interesting experimental writing because it's a technical paper, and it's actually a historical paper, okay, because it actually gives the history and the development of the ideas in a much more intuitive way. You know, when I wrote this in 1991, I was still a pretty young guy, and you know how it is when you first create something, it seems very complicated, right? And to me, in 1991, I did not know how to really explain this simply, right? And hopefully I've explained it well to you today, and hopefully enough that maybe you'll be interested in looking at the paper, okay? So that's it. Thank you very much. Questions?
If I got it well, in your notion of condensed context, so you look at prefixes of some string, and you have two steps in dynamic programming and KNP. Would it be appropriate to look, instead of prefixes, to look at factors in your string, and using a kind of notion like the absent words or forbidden words that you have in the string?
It's an interesting idea. I'd be delighted if somebody would pursue it. Mm-hmm. It's an interesting idea. Yeah, I mean, in 1991, I had my hands full doing that. I was quite happy when I got, when I got to the end that I actually got a result. So, but yes, I mean, it's part of the reason why I decided to give this talk to you guys in particular, which is that I thought it might be interesting and might actually stimulate you guys to move in a direction. I can see some things kind of going that way, but I really I just wanted to put this in front of you, and you know, all you young folks, you know, go after it. Okay, all right. See if you can do better. Okay. Another conjecture I have actually, though, with respect to doing better is I mean, I hate lower bound proofs, so I wouldn't even go near it. But I have this idea that in some sense it's this is nearly optimal. Okay, and so that's an interesting question, right? Can you do better? Okay, or can you show that you can't do better? That basically this is as close to, because if you think about that bound, I mean, it crosses 1 at 56%, right? At 56% identity on a 20-letter alphabet, that's almost random, okay? So if your level of stringency for your match is such that you expect to find a match at random, right, then you know you have to scan the whole text, right? Okay, and I'm almost there. I'm really close to the point where that's a random hit. Okay, right? And the fact that I go over 1 at 33% is just because that was the best bound I could produce. But if you actually computed the number of edit scripts and could compute them exactly accurately, right, would that line would cross further out. It might cross, in fact, exactly at the point where it might hit 1 at exactly a random match, which for DNA is 48%, right? I'm at 33% on an equidistributed alphabet DNA. It's 48%, I think, 48, 47%, right? So it's another kind of conjecture, right? So if you were to try a lower bound proof, I'm sorry, please.
So, okay, can you hear me? So if you map the camera from the same neighborhood to the same entry of the hash table, so you wouldn't need neighborhoods because you see what I mean? I mean, if you could map a k-mer to the same entry of the hash table that the neighboring k-mers, then you basically would not need neighborhoods because you would have the same. I mean, you just
right. So if you can figure that out, that'd be cool. Mm-hmm.
Yeah, but of course it's not possible because neighborhoods are not disjoint. So you cannot do it like this. But still, you can maybe partition k-mers into kind of non-intersecting classes. Let's say each class mapping to the same entry of the hash table, so that you would reduce the computation of neighborhoods somehow, or maybe even completely get rid of them. I don't know. So
yeah, I mean, I think there's still a lot of
to replace the computation of neighborhood by a smart hash function. So that's basically the idea. So
yeah, and I think that's what kind of both Galil and Alberto are alluding to. Is there some way to do that? The only thing that I've seen that kind of goes there is Udi Mamber wrote a paper where he had this kind of magic wildcard phi, and then he considered all of the things that involved phi and allowed you to do the one neighborhood particularly efficiently as a kind of a hash, but I've seen no generalization of it to more than one letter.
Okay,
but it's an interesting idea, right? But the surprising thing though is that there's a point where if you go to too big a neighborhood, right, it falls apart. But what's interesting is that it's better than exact matching because of the increase in specificity, right? It's even though you're generating more words, right, the specificity of each match is so much higher, right? So that kind of, if you think about it, you step away from exact, it goes down, right, and then it'll start to, but that epsilon log sigma n, that's it, okay? That's the sweet spot, okay?
So this is a more human interest question. So BLAST's been tremendously successful, but since then there's sort of a lot of tricks and new data structures and so on developed in this community and elsewhere. In my observation, not a lot of them adopted by bioinformatics. Some of them, but not others. For young and not so young people in algorithms that want to have an impact in bioinformatics and biology, what's the best way to get the latest data structure adopted, and what's worked for you?
Well, I mean, if you want to have impact, you have to have solve a problem that's of interest to the biologist. Okay, so you know, solving a problem under Hamming distance isn't useful. Solving a problem under unit cost. I mean, you know, the reason BLAST was a winner was really twofold. One is that it was for protein matching, which is something that was interesting under generalized Levenshtein measure. And I think actually the other thing that made BLAST hugely successful was that we had a measure of significance for hits. So the scientists knew immediately, like whether, because there was much overinterpretation of hits prior to that. Okay, so yeah, I mean, it's, you know, it kind of gets into what's called algorithm engineering, right? And I mean, I love that stuff, right? I do it. You know, I write C code. I think about the hashing behavior of the machine. There's an L1 through L3 hierarchy, and you have to really get in there, okay? And something that this kind of community doesn't do that much, okay? But I would say the main thing is just, you know, you have to solve the problem as the scientist sees the problem, not as you want to see it as a mathematician. I'd say that's the main take home, right? To have impact to a customer, you have to solve the problem that the customer has, okay, not the problem that you can solve, right?
Other questions?
Mm.
I have a question actually that is a follow-up on this question. So how does it translate into the realities of BLAST with amino acid matrices and with similarity rather than distance? It's not immediately.
Say again, Pavel.
You describe very nice model for epsilon similarity, but in reality you have to apply it to amino acid matrices. You have to transform from distances to similarity measures, and all these details. How do they feed this elegant model, or do they create messiness? Or
well, the generation of neighborhoods with respect to a different measure, you can't use the KMP and the estimate, but you can still do the core algorithm, right? Which was the first one that basically just computes the dynamic programming matrix, and the other problem, of course, is you don't have a monotonic increasing function. So, but you still basically just enumerate the words with respect to the trie. And that's what we did. And the other thing that was actually, is it was also with respect to a Hamming model. There were no insertions and deletions. There were just substitutions. And under that case, there were enough constraints that, again, generating the neighborhood was pretty easy. But, yeah. But the result that I showed for Levenshtein, simple Levenshtein, is very specific to simple Levenshtein. You're going to lose some of the things, okay, like monotonicity, et cetera. So some of those properties go away. You can still generate the neighborhoods, but it takes more time. You have to, the basic principle of enumerating the trie, right, with respect, but you have to enumerate the whole trie under a non-monotonic measure, right? I mean, I think you can explore the space. It's fairly simple. The main idea is, yeah.
Is